Okay, so in this example, I want to show you for case 2 for regular singular. Okay, case 2 where our indicial roots are equal. Okay, let's say we have x y double prime plus y prime minus 4y equals to 0 near regular singular point at x equals to 0. So to show that this is a regular singular, first we have to check the p. From here, our px here is equals to x. So that means when p0 is equals to 0. So since p0 is equals to 0, so we can say that x equals to 0 is a regular singular point. And we want to check to show that this is a regular, so you have to use these two limits. Limits x q over p, and then we get equals to 1, so therefore this limit is exists, and this limit x squared times q over p, and we get 0, so therefore this is also exists. Hence we can say that x equals to 0 is a regular singular point. Okay, from here we got the a and b, so you can find r by using this formula, this equation. Okay, and then we find y prime and y double prime, and then substitute back. Okay, but before that I would like to review these two proof because we will be using this later. And for number 1, so let's say if we have y equals to a naught xr fr, then dy dr, we will get this. So how? So this is the proof here. Okay, we have y equals to a naught xr fr, and then we put log on both sides. So log y equals to log a naught xr fr. Okay, by using the properties of log, when the function itself multiply, so we can separate them. So we can get log a naught plus log xr plus log fr. Again, by using the properties, r, since r is the power here, you can put it to the front. So we get log a naught plus r log x plus log fr. Okay. And then we differentiate y with respect to r. We differentiate both sides with respect to r, and then we will get, when we differentiate log y, we will get 1 over y dy dr. When we differentiate log a naught, since a naught here is a constant, log a naught is a constant, so we will get 0. Differentiate r log x with respect to r, and we assume log x here as a constant. So we get log x plus differentiate log fr, so we will get f prime r over fr. And then we want dy dr, so we bring y to the right, or we multiply both sides with y, so we get y log x plus y f prime r over fr. And then we can substitute again y, since our y here is a naught xr fr, so we substitute this y into a naught xr fr multiply f prime r over fr, so we can cancel fr, and we will get y log x plus a naught xr f prime r. Okay, so this is our dy dr. This is the first proof. And the second one is, if we have fr is equals to 1 over a plus r power of m multiply with b plus r to the power of n, multiply c plus r to the power of p, then we can say that f prime r is equals to negative 1 over a plus r power of m multiply b plus r power of n multiply c plus r power of p, and we multiply again m over a plus r plus n over b plus r plus p over c plus r. Okay, so how can we get this? This is the proof here. Okay, again, let's say if we have this, so we want to find the f prime r, that means we have to differentiate. But before that, to differentiate, we have to put log on both sides first. Put log here, and we'll get this. Again, by using the properties of log, since log, we know that log a over b, we can get log a minus log b. So this is what we get. Okay, so log 1 minus log this. Okay, again, from the properties of log a b, so we can get log a plus log b. So apply it, so we can apply it here, since this is a multiply. Okay, 1 term, 2 and 3, so we multiply this. If we use these properties and we multiply with negative here, so we will get log 1 minus log a plus r minus this and minus this. Okay, so since log 1 is equals to 0, and power we can bring to the front, so we get negative m, so bring n to the front, bring p to the front, this is what we get. This is log fr, ln fr. Okay, and then we want to find the f prime r. So if we differentiate, again we differentiate d dr, right? We put d dr on both sides. So if we differentiate fr, we will get f prime r over fr. And if we differentiate log a plus r, so negative n is constant, we will get differentiate log a plus r is equals to differentiate a plus r respect to r, so a is constant, and we will get 1 over our function again, a plus r. So this is what we get. Multiply with negative n, and same here, and also here. Okay, so from here we can multiply both sides with fr, and so we will get f prime r is equals to negative here. Okay, I bring this negative to the front, negative fr is equals to this again. And what is our fr? Fr is equals to this. This is our fr. So substitute again into this, multiply with this. Okay. Okay, so I have shown you these two proofs, and we will using this later. Alright. So now let's look back to our problem here. Okay. And again, as usual, we have found we have to find our y by using the Frobenius method. Okay, so an adds to the n plus r, and y prime and y double prime here. And then we substitute again into our problem here, x y double prime plus y prime minus 4y equals to 0. So this is what we got. Since this multiply x, wait, yeah, x y double prime. So suppose it have x here, but and this is n plus r minus 2, so minus 2 plus 1, we get minus 1, plus y prime minus 4y, y prime minus 4y equals to 0. And then we shift to the lowest power of x. So since we have n plus r minus 1, n plus r minus 1, and n plus r, so we have to shift this to be n plus r minus 1. So we have to substitute. Our r now has become, our n now has become n minus 1. So n minus 1 plus r, originally n here is equal to n minus 1, and n equals to n minus 1 equals to 0, therefore n minus 1 equals to 0, therefore n is equals to 1. Okay. So since we have all our x terms here with power of n plus r minus 1, so we can rewrite it to get this. And then to find the indicial equation, again we can use when n equals to 0, and then we substitute n here. So we will get r squared a naught equals to 0, where a naught cannot be 0, therefore r equals to 0. So r squared equals to 0 and r equals to 0. So this is our indicial root, r1 equals to 0 and r2 is equal to 0. Since r1 is equals to r2, that's why we use this. We say that this is a case 2. Okay, and then again, you have to find the recurrence relation from here. N plus r squared an minus 4an minus 1 equals to 0, and then you will get an equals to 4an minus 1 over n plus r squared. After you get the recurrence relation, you can find the n, substitute n with 1, 2, 3, and so on, and then you will get a1, a2, a3, a4. And if you notice here, our a1 in terms of a naught, a2 in terms of a naught, a3 and a4 are in terms of a naught. And then we substitute again into our y, where y is equal to a naught xr plus a1 x1 plus r, or we can factorize x to the power of r, so we get a naught plus a1x plus a2x squared and so on. And then we can put our a1 here is 4 over 1 plus r squared, a2 is 4 squared over 1 plus r squared times 2 plus 2 squared and so on. Just substitute again. So our solution for y1, and then we substitute back r equals to 0 into this, we will get y1 is equals to, just substitute r equals to 0. So therefore 1 plus 0, 1. 1 plus 0, 1. 2 plus 0, 2. Square and so on. This is our y1. After we factorize all the, after we simplify. Okay, to find our y2, okay, so if y1 is equals to y1 this actually is equals to a and x r xn plus r1, where our r1 is equals to 0. But to find y2 is you have to differentiate y. So you have to differentiate over y1 here. Okay. And then we substitute r equals to 0. So to differentiate, y, okay. So to differentiate this y, as I've shown you on the first part, y equals to a naught x r fr, if I want to find it dy dr, and I will get a naught. Okay. Okay, so this is what we got. Dy dr equals to y ln x plus a naught xr f prime r. Ln x plus a naught x r f prime r. Okay. Now here actually. So this is our fr here. This is our fr. Okay, a naught xr fr. Everything in this bracket is fr. So you will just have to find the f prime r. That means you have to differentiate this. Differentiate 1, you will get 0. Differentiate 4 over 1 plus r squared. So you will get this negative. You bring negative 2 times 4x 1 plus r minus 1. Okay, and then to differentiate this, again we have to use the second proof deduction earlier. So you will get this, or you can also use product rule here. That means 4 squared 1 plus r power of negative 2, 2 plus r power of negative 2. So to differentiate this, you can use product rule. Okay, from here, you can use the proof deduction, and you will get this one, and also this, you can use the proof. So that's all. If you have found our dy dr, so substitute r equals to 0 into this, and so we will get this one.